So chapter 2 is about graphical summaries of data. When we have a bunch of numbers, especially when it's a really large data set, it's a good idea to summarize the data graphically so that someone can just look at a quick picture of the data and get an idea of what's going on with the data without having to look at all the individual numbers. So here's an example of a set of categorical data. I have 132 Stat 1200 students this semester, and they fall in the following grade levels: freshman, sophomore, junior, and senior. Grade level is a category. So even though grade level is a category, I do have numbers associated with each of those, which is the frequency or how many students I have in each of those grade levels. So one thing that can be done with this is to turn it into a bar graph. We're simply going to make a bar for each one of these four classes, not classes, but we're simply going to make a bar for each of these four values of grade level, and then the height of the bar will equal the frequency that we see over here. So that gives us a bar graph looking something like this. Oftentimes it's useful to turn the frequencies into relative frequency, or you could say percent, or you could say proportion. You do this by dividing the frequencies by the total frequency. So there's a total of 132 students. If you take 109 and divide by 132, that tells you that 82% of my Stat 1200 students are freshmen. And you can do that with each of these values of the grade level variable, and then do a bar graph where the y-axis is relative frequency instead of frequency. And it's essentially the same picture that we saw before. The main reason that one would want to do relative frequency is if you're comparing two sets of data. For example, if I wanted to compare the distribution of grade level in Stat 1200 with the distribution of grade level in Stat 2260, I could do a couple of bar graphs side by side, but if the y-axis is the same on both of them, the bars for Stat 2260 are going to look very, very tiny because I only have 30 students in Stat 2260 and I have 130 students in Stat 1200. So if I do this comparing frequencies, that's not going to really be the comparison I want. So doing it with relative frequencies is one of the reasons why we do relative frequency, is to compare two sets of data like that. Also, once you have relative frequencies, you can do something called a pie chart. So we have a circle, which is split up into sectors, and each one of these sectors is sized proportionally to the proportion of the value of the variable that it represents. So this chunk over here represents the freshmen, so that's 83% of the circle. And this chunk here represents the seniors, and that's 5% of the circle. Just another way of graphing categorical data. Then we turn our attention to numerical summaries of Then we turn our attention to graphical summaries of numerical data. Okay, so for example, during the 2019 season, these are the numbers of home runs hit by players on the Los Angeles Dodgers. So this is numerical data, and we would like to summarize these numbers graphically. One way to do that is with a stem and leaf plot. With a stem and leaf plot, we basically have a vertical bar with stems on the left side of the vertical bar and what we refer to as leaves or leaves on the right side of the vertical bar. In this case, the Dodger home run data is mostly two-digit data, so we just need stems to represent the tens place, 10s, 20s, 30s, and 40s, and then the leaves will represent the ones place. So notice this is not 11 home runs or 112 home runs. This is one player that had one home run, and this is another player that had one home run, and another player that had two home runs, and another player that had three home runs, and so on. And down here, when the stem is 1, we're now talking about numbers in the teens. So this is a player that had 11 home runs. This is a player that had 12 home runs, the one from here and the two from here. Here's another player that had 12 home runs, the one from here and the two from here. And this is the player that had 15 home runs, the one from here and the 5 from here. Here's another one that had 15, one that had 17, one that had 19. So it compresses how much space the numbers take up because you have all these numbers that start with a 1. Well, I'm only writing that 1 once right here. And then usually off to the side somewhere, there's a legend or a key that is letting us know, in this case, a 4 with a vertical bar and a 1, that equals 41. So that's letting us know that this is the tens place and this is the ones place without having to write that out in words. You can also do a stem and leaf plot with numbers that are not whole numbers. For example, suppose we have some data on students' GPA. So now all of these numbers are 1 point something, 2 point something, 3 point something. So now the stems over here on the left side are going to be the ones place, and the leaves are going to be the tenths place. So this 5 right here represents that one of these students has a grade point average of 2.5. And this 5 right here represents that one of these students has a grade point average of 3.5. And again, you see the legend down here is telling us that when we have 3 on this side of the vertical bar and 6 on this side of the vertical bar, that represents the number 3.6. Oftentimes when some kind of computer software is creating the stem and leaf plot for us, this is the exact same stem and leaf plot, but what I've changed is these leaves are in numerical order. Usually when computer software creates a stem and leaf plot for us, it puts the leaves in numerical order like this, not in the order that they appear in the data set. And also, when you are asked on the homework to create a stem and leaf plot, you are going to be expected to put the leaves in numerical order like this. Then there's a variation on a stem and leaf plot referred to as a back-to-back stem and leaf plot. Suppose, in addition to having information on the Dodgers home runs, suppose I also have data on the Angels home runs from last season. So that's these numbers right here. So if I was to cover this up, if I was to cover this part of the stem and leaf plot up, this is exactly the same stem and leaf plot we had earlier for the Dodgers. But now on the left side, I have leaves for the Angels. So I'm still using the same stems, but now I have leaves going in either direction, one side for the Dodgers, one side for the Angels. So this 7 right here represents a player for the Angels that had 17 home runs. The stem is 1, the leaf is 7. This 7 over here represents a player for the Dodgers that had 17 home runs. The stem is 1, the leaf is 7. So this 3 and this 2, don't read that as 32. You read the stem first, so that's 23. It's a great way of comparing two sets of data. Another type of graph that I really like a lot is a dot plot. All you have to do is draw a number line and then put a dot on the number line for every one of the numbers in your data set. So for the Dodgers data set, we had two players that had one home run. So I've got a pile of two dots at the number one on the number line. And then there was one player that had two home runs and one player that had three home runs and so on. There were two players that had 12 home runs. So you see a pile of dots there. And so all you need is a number line and start piling up the dots above each number in the number line representing the numbers that are in your data set. Also notice I keep referring to this as a number line. I need to have all these numbers on the number line even if there's no data associated with it. If there's a gap in our data, then I need to see a gap in our graph. Okay. Similarly, up here with the stem and leaf plot, same type of thing. If there was nobody that hit 20 something home runs, I would still have to have a stem for the 20s. So that's a dot plot. One of the things I love about a dot plot, let me see if I can bring this one up, is that dot plots, since they're not actually displaying the numbers, this here is a dot plot of 10,000 dots. And you can see way down here, you can see the individual dots, but over here the dots are piled up so tightly that it just looks like a black line going up. But again, dot plots allow you to display tons of data in a relatively compact space, and it allows us to start seeing a shape of the data, which we're going to talk about a little bit later. Next up is a histogram. Histograms are used all the time to display numerical data. So it's a two-step process creating a histogram. First of all, you have to create a class frequency table. For our Dodger home run data, we're going to construct classes with a width of 10 starting at 0. So, sorry about that. So 0 to 9, 10 to 19, 20 to 29, and so on. And then we have the frequency within each class. So there were 8 Dodger players that had 0 to 9 home runs. 7 Dodger players had between 10 and 19 home runs. One player had somewhere between 40 and 49 home runs. Now, before I go on, I should say I'm showing you this notation because this is what they use in the book and in the homework, but I do not like this notation at all because when we draw a histogram, the bars, you're going to see in a second, the bars should touch each other because the entire x-axis is covered. So if the histogram bars should touch each other, the histogram classes should touch. So this class should end where the next class begins. So I prefer to do the classes using inequality notation. X is equal to 0 and up to but not including 10. And then X is including 10 and up to but not including 20, and so on. That's the way a lot of the graphing calculators do it, and that's the way I prefer to do it. When I see classes like this, I often think to myself, what if I had a number that was 9.5? I know it's not possible to hit 9.5 home runs, but if we had the number 9.5 in our data set, I don't have a place to put it if this class ends at 9 and that one begins at 10. So I prefer this notation, but our book does not use that notation. So now we create a bar graph, but this time with the bars touching, and still the height of the bar matching the frequency within each class. So from 40 to 49, we had one player that hit somewhere between 40 and 49 home runs, and that bar has a height of 1. So that's what a regular frequency histogram would look like. Also, you could create this histogram by adding a column to the class frequency table that shows relative frequency and create something called a relative frequency histogram. I'm not going to show that here, but it would be created in the same way. The only difference is these numbers on the y-axis would be decimals corresponding to the relative frequency. Also, there's no magic to what the numbers I should use as the classes, as long as all of the data has a class to fall into. So in other words, we have players that only hit one home run, so I've got to have a class that accommodates them. And I had one player who hit 47 home runs, so I have to have a class that accommodates that player. Other than that, the only thing that matters is that all the classes have the same width. So in this case now, instead of starting at 0 and having a width of 10, now I'm starting at 1 and having a width of 12, which is giving me 4 classes now instead of 5, but still a very similar looking histogram. Okay, now with histograms and dot plots, we get to talk about the topic of shape. Both of these histograms of Dodger home runs have a similar shape, which statisticians call skewed to the right. So there's a big pile of data on the left and a tail going to the right. This is the sharp end of the graph, or the pointy end of the graph, or the skewer end of the graph. So it's skewed to the right. And this happens a lot. This happens with a lot of sets of data, especially data involving money, where you have a bunch of people's income piled up near zero, relatively speaking, and then fewer and fewer data the farther you get out here. A lot of data ends up looking skewed to the right. But sometimes the opposite can happen. For example, if I gave a quiz and the quiz was really easy, I would expect a pile up of scores that are near 100%, and then very few scores down here in the lower percentages. So a lot of times data will be piled up to the right with the tail going to the left, and that would be skewed to the left. And then finally, especially later on in the class, chapter 6, 7, 8, and 9, we see data a lot that looks symmetric. And usually when it looks symmetric, this is the type of symmetric shape that we see, with a whole bunch of data in the middle and a little bit of data going out in this direction and a little bit of data in this direction, but the majority of the data piled up near the middle. For example, we see this a lot with almost any kind of testing data like IQ scores and stuff like that. Whole bunch of people piled up near average, and then a very few people out here with really high IQ and a very few people down here with really low IQ. So there's a lot of data that follows this kind of symmetric shape. There's a lot of other types of shapes that we could talk about. There's something called uniform, there's something called bimodal, and there's a lot of others, but this is the 3 big ones that we need to worry about for chapter 2. Okay, time to go attack the chapter 2 homework.